Well, we've already seen that light travels at 3 times 10 to the 8th meters per second in a vacuum, extremely fast. It's a little bit slower in mediums. Galileo was maybe the first person to seriously try to measure the speed of light. And he knew that it was faster than sound. He figured he would use speed equals distance over time. And he came up with a reasonable method to do this. He had an assistant, and he sent his assistant to a hill far away, a known distance away, something like 10 or 15 miles. And his assistant had a lantern, and so did he. And they had this all figured out. They waited until night, turned on the lanterns. All right, they could see each other's lantern far away in the distance, but there weren't that many lights then. So they could tell when the other's lantern was on or off. And they put covers over the lanterns. And Galileo would start, he lifted the cover off, and he had his hand on his finger. They did not have good clocks then. Very likely he used his pulse. He did in some experiments, he used his pulse as a timer. So at the instant he releases the cover, he starts taking his pulse. Now, the speed of sound, sound takes something like 5 seconds, a little less than 5 seconds to go a mile. So if the distance is 10 miles there, that's going to be 50 seconds. And if it's another 10 miles back, now we're talking about 100 seconds, close to 2 minutes. Now, Galileo knew that light is faster, much faster, but he figured, okay, instead of 100 seconds, maybe it's 10 times as fast, in which case it would still take 10 seconds to go there and back, for example. So he figured, okay, I'll take my pulse, and it might be around 10 pulses, 8 or 9 or 10 or 12, something like that. So he's figuring, okay, the light is traveling now, and it's going to take a little bit more time for the light to get all the way to this hill, 10 or so miles away. And now when his assistant sees the lantern, that means the light has made it there. So now the assistant is all ready, and he takes the cover off of his lantern, and now that light starts traveling back toward Galileo. And the light gets to Galileo. He sees the light, and then so now he has counted how many pulses. And they worked on this. I don't know how many times they actually, how many trials they did. But Galileo was pretty smart, and maybe his assistant was smart also. And they realized that, after a while, they were not measuring the speed of light. They were basically measuring their reaction times. The reaction time of the assistant from when he saw the light to when he was able to take the hood off of his lantern. And then Galileo's reaction time, I guess, and how accurate his pulse was. And not even that, just measuring reaction time. Right. So ideally they would put this in. They got a very small time, I don't know, like 1 or 2 pulses or something for the time. And he knew the distance, but the time was very imprecise. All right, light's just too fast. In the 1850s, a scientist named Fizeau came up with a mechanical method of measuring the speed of light. And he was successful in this, and he actually did this in the lab. So he has a gear, they call it a toothed wheel, rotating around, and he shines light at it, and he can adjust the speed of the motor that's turning the toothed wheel. There's a mirror behind it, so the idea is that the light goes through between teeth. Now it's being blocked, but the beam that went through continues on, hits the mirror, bounces back, and now at some little while later, there's an opening there, and the light can go through again, and he sees it. So he adjusts the speed of this wheel until it's pretty much adjusted so that the light is traveling the distance between the wheel and the mirror there and back in the time it takes for the wheel to rotate from one tooth to the next tooth. So now he does this with a lot of teeth on here and a very, very fast wheel. And it's not just a short distance, it's a very long distance here. And he's able to come up with an approximate value, somewhat the correct order of magnitude, something times 10 to the 8th meters per second. And since that time, we've refined this considerably. The modern way to figure out the speed of light is to use a different approach, use the wave aspect of light. Kind of like we're doing in lab to measure the speed of sound. We take advantage of the wave aspects of sound. And it's a much better way of measuring the speed of sound and much better way of measuring the speed of light. Light travels slower in different material media, such as water, glass, etc. And this is how we formulate, this is how we approach this. We take the ratio of the speed of light in a vacuum over the speed of light in the particular material. And that ratio we call the index of refraction of that material. So different materials have different indices of refraction. Now, the speed of light in the materials is always going to be slower than the speed of light in a vacuum. So this ratio is always going to be greater than or equal to 1. Now, air, we're most used to light traveling through air, very, very close to the speed of light in a vacuum. And so this index is very, very close to 1, just slightly greater. For all practical purposes, well, for a lot of practical purposes, it's the same. For our problem solving, we'll assume it's the same. There's a table in the reference tables with the indices of refraction of various materials, a few samples. All right, so air, corn oil, just like the name says, diamond, ethyl alcohol, 2 different kinds of glass, glycerol, lucite is a solid, plastic, transparent. All these materials are transparent, of course, to visible light. Quartz, the mineral, sodium chloride, that's table salt, water, and zircon. So which material has the highest index of refraction? Diamond, very special material, hardest natural substance and very high index of refraction. There are other materials with higher indices of refraction, but they're kind of flaky. Let's see, the 2 glasses have slightly different, well, significantly. There are other types, many types of glass, depending on the impurities in it and the manufacturing process. Which material has the second highest on this table anyway? Zircon, and cubic zirconium is imitation diamond. Diamonds, the sparkling of diamond, the reason that they look so sparkly is due to this high index of refraction. Sample problem, calculate the speed of light in lucite. Okay, we'll use n equals c over v, and we're trying to solve for v, speed of light in the material. So that's c over n. All right, now we're going to look up on the reference tables for lucite. N is 1.50, so we'll substitute that. Speed of light in the vacuum over 1.50. Notice no units. Don't put units on. And we get v equals 2 times 10 to the 8th meters per second for the speed of light in lucite. Still extremely fast. How much a light ray refracts depends on the relative difference or ratio of the indices of refraction of the 2 materials. And we'll be studying this in some depth, learning the law of refraction. And so since the index of refraction depends on the speed of light, how much it refracts depends on the relative speed of light in the two materials, how much light speeds up or slows down when it goes from one medium into another. All right, so speed of light in a vacuum, 3 times 10 to the 8th, approximately very close to the same speed in air. Index of refraction, n, equals that ratio, c over v. And the speed of light in a material is related to how much it bends when entering or exiting that material, or how much it bends is related to the speed of light.